Good morning, everyone, and welcome to this lecture. This is lecture number 2, and we are dealing with transfer of heat or heat transfer. In the previous section, in the previous class, what we had gone through? The previous class, we had gone through the different modes of heat transfer, and we had specifically targeted the first mode of heat transfer, and the first mode of heat transfer is known as conduction. And we had seen the formula of conduction of heat delta Q by delta T, which is the rate at which the rate of heat flow is directly proportional to change in temperature, depends on the material, directly proportional to area, and so on. And we had formulated the formula delta Q by delta T is Ka by L, theta 1 minus theta 2. This formula is only valid for steady state. What do I mean when I talk about steady state? And steady state, the temperatures of different sections, they are different from each other, but they remain constant with time, and the temperature gradient also remains same. Do we understand this? Do we remember this?
Yes, sir.
We had also seen the differential form. The differential form of this equation, and the differential form of this equation is valid whether the state is steady state or variable state. Dq by dt is minus ka d theta by dx, where negative sign indicates that in the direction of heat flow, temperature always decreases. We remember this. Then we had seen the thermal resistance L divided by Ka. This is doing the same job as electrical resistance does in electric current. Therefore, dq by dt or delta Q by delta T is also known as electrical current. Electrical current flows because of temperature difference. Sorry, electrical current delta Q by delta T is taken as thermal current or heat current. It is same as your electrical current. Electrical current flows because of difference in voltages or potential difference. Thermal current flows or heat current flows because of difference in temperature. Whatever job this resistance is doing in electrical current, the same job this rod is going to do. As you can see, the formulae are exactly same. We had also seen a comparison between the two, electrical conduction and thermal conduction. Both of them are exactly same things, whether you take them as electrical conduction or you take them as thermal conduction. Both are exactly same. Do we understand this? Yes or no? No or yes?
Understood, sir.
Everyone understands this?
Yes, sir.
Now, since we understand this, we can now move on to the next heading. And the next heading, I think we have done questions on this as well. I think we have done questions on this. So the next heading will be combination of conductors. So you can write the next heading, combination of conductors. Combination of conductors. Now, if I may ask, what do you mean by this combination of conductors? Yes. What will you mean by combination of conductors? Yes.
Series combination and parallel combination in current, it is same like that.
Yes. Series parallel and parallel combination in current. This combination is the thermal analog of the same. What do you mean by thermal analog? So there will be two types of combination that we are going to deal with. What will be the two types of combination? The first one, let me call it as A, the series combination. Series combination. What happens in the series combination? If I talk about registers, these are the two registers R1 and R2. The current flowing them would be same, but the potential drops would be different. Do we understand this?
Yes, sir.
Current is same, potential drops V1 and V2 are different. You can replace these two registers by a single register are equivalent. The current will be EI and the potential drop would be V. You know that this V will be V1 plus V2, yes or no?
Yes, sir.
Or this V can also be written as I into R1 plus R2, yes or no?
Yes, sir.
Or your R equivalent becomes equal to R1 plus R2. Do we understand this?
Yes, sir.
I've taken the example of I've taken the example of only two registers. That could be three or four. Doesn't matter. Now this series combination is going to come here. This is going to come again in capacitor. This is going to come again in resistor. This is going to come again in inductor. Everything remains same. Do we understand this?
Yes, sir.
So if you understand it once, we should be able to make it out. So now you have slabs arranged here. Whatever heat current flows in this slab, same heat current will go through this slab, same heat current will go through this slab. Remember, we are talking about steady state. Heat current delta Q by delta T. Heat current is same. The heat flowing per unit time or heat flowing is same. Do we understand this? Yes or no? No or yes?
Understood, sir.
The only thing that might look a bit different is that at all the points we have at all the points we have temperatures here, theta 1, theta 2 and so on. Theta 1 is the temperature of this point, theta 2 this point, theta 3 this point. Here also I can write the same thing, but we don't normally write it V1, V2 and V3. So we write it like this. Do we understand this?
Yes, sir.
Heat current flowing through all the rod is same. So if I find the heat current through the rod 1, that will be equal to heat current through the rod 2, that will be equal to heat current through the rod 3 and so on. Yes or no?
Yes, sir.
First listen to me, then you can write it. I'll give you time to write it. Right? Heat current will be same. Now we can replace these rods by one rod and I can find the equivalent resistance of that rod. Yes or no?
Yes, sir.
R equivalent will be equal to R1 plus R2 plus R3 up till Rn, where R1 will be the resistance of the first rod L1 by K, L1 by K1 A1, L2 by K2 A2, and so on. We understand this? Yes or no? No or yes?
Yes, sir.
You can make a shortcut formula if you want to. The shortcut formula would look like this. I don't know how much will it help you, but you can make a shortcut formula like this as well if you want. Let me try to put it in the space. You can make the equivalent formula like this. Do we understand this? Yes or no?
Yes, sir.
Now I'll give you 2 minutes to note this down. This is the series combination. Heat current is same. The potential difference across each rod is different. 2 minutes, note it down. This was the series combination of registers. You can also note these points. Uh, Sometimes they ask you equivalent thermal conductivity. I've also seen question of this equivalent thermal conductivity in a JEE. That does not make much sense, but then they take the length the length as same. I don't the length of each section as same and area of each section as same. So L1, L2, L3 all become L. So N times L divided by L by K1 into A, all the cross sections areas are equal, then you can get this equivalent thermal conductivity. Do you understand this concept of equivalent thermal conductivity?
Yes, sir.
I could never understand this. Congratulations if you have understood this. And one more thing they are going to ask, and we are not going much into detail, is the temperature of the interface. Now, what do you mean by interface? Interface is this junction. Now, in current, they might not ask you the potential of this point, but in thermal physics, you will be asked to find out the temperature of this point theta, which is the interface between two slabs. One end of the slabs is maintained at temperature theta 1, the other end is maintained at temperature theta 2. So how will you find out the temperature of this interface? It's very simple. The heat current is same through both of these, yes or no?
Yes, sir.
From there, you can just find out the value of theta, and a very simple answer comes here, which you should remember rather than solving the entire question. And this is the simple answer that appears. So you must remember this answer so that you don't have to write the equation again and again, and you can get away with this. Do we understand this? I'll give you a minute to note it down. Do it. The next is parallel combination of rods. In parallel combination, you must understand the two registers just for the sake of argument, R1 and R2, and the potential difference V1 and V2. The potential drop is same. Do we understand this?
Yes, sir.
The current I1 and I2 are different. Here, the total current I which flows in this circuit, total current I will be equal to I1 plus I2. Do we understand this?
Yes, sir.
V1 minus V2, which is the potential difference, will be equal to I1 into R1 will be equal to I2 into R2. Do we understand this?
Yes, sir.
Or this V1 minus V2, which is the potential difference, can be written as I multiplied by R equivalent. Do we understand this R equivalent? This 1 by
Yes, sir.
R equivalent is equal to 1 by R1 plus 1 by R2. Anyone understands this?
Yes, sir.
Now, similarly, you can have the parallel combination of a number of slabs. Now, for this parallel combination to work, the length of the slabs has to be same. Otherwise, it becomes a problem. We understand this, no? The length of the slabs has to be same, and they must be having the same temperature difference across them. So, the parallel combination will look something like this. Do we understand this? Yes or no? No or yes?
Understood, sir.
Then their equivalent resistance can be given by 1 by R will be equal to 1 by R plus 1 by R2 and so on. Do we understand this?
Yes, sir.
Through all this parallel combination, different heat currents will flow. Yes or no?
Yes, sir.
The total heat current delta Q by delta T will be equal to summation of delta Q I by delta T. Do we understand this?
Yes, sir.
Temperature gradient across each slabs would be same. Do we understand this?
Yes, sir.
Total thermal current, we'll write it here, will be given by this. Let me try to get it. Since they've written it in 3 or 4. uh, So, total heat current could be written like this. Yes or no? So you can have this effective thermal conductivity. Are you able to understand what is written here?
Yes, sir.
The thing on the left hand side, which is this one, this is this is the total heat current dq by dt. Do we understand this? And on
Yes,
the
sir.
right hand side, we have delta q1 by delta t, delta q2 by delta t, and so on. We understand this? Yes or no? No, yes.
Understood, sir.
And the formula becomes the formula for equivalent conductivity. They've asked it many times, this equivalent conductivity. And so I have given you this one. Temperature gradient would be same. So fatafat note it down so that we can move ahead and solve some questions on this. This is a very famous question. This has come many times. So basically what is there? You have a, I mean, hill resort, Himachal Pradesh, somewhere where there is freezing temperatures. Outside temperature is there. It's given minus 20 degrees Celsius. Inside temperature is to be maintained at 25 degrees Celsius. So they put a lot of laggings and lot of different materials so that the house keeps warm. You have to find the interface temperature T3 and T4. This question may look very lengthy, but the solution is very simple probably. Do you understand how these slabs are connected? Yes or no? Huh?
Yes, sir.
You have 2 minutes to give me the answer. If I call the resistance of this one as R1, this is R, this is R, this is R2. My R1 will be equal to L1 by K1 into A1. The length is given as L. The thermal conductivity is given as K. Area of cross section is A. This is R1, L by Ka. R2 will be equal to L2 by K2A2. L2 is 5 times L. This is 5 times K into A. So this is also equal to R1. Both are equal to R1. Now the question is pretty simple. I have this resistance as R1, this as R, this as R unknown, and this as R1. This temperature is given as 25. This temperature is given as 20. This temperature is given as 25. This temperature is given as 20. You can call this one as theta 1. You can call this as theta 2. This is given as minus 20. If I call the current here as I, you can write the value of I as 25 minus 20 divided by R1. You know the value of R1. That will be equal to 20 minus theta 1 divided by R. Once you know the value of I, you can find out the value of R. That will be equal to theta 1 minus theta 2 divided by R. That will be equal to theta 2 minus 20, that is plus 20 divided by R1. Everything is known and you should be able to get the answers from here, from these equations, from any part of this equation. The first thing you can calculate is from this equation, and from this equation you can calculate the value of theta 2. Yes or no?
Yes, sir.
Once you get the value of theta 2, you should be able to calculate the temperatures of the interface. Yes or no? No or yes? Once you get the value of theta 2, you can put the value of theta 2 in this equation and get the value of theta 1. The answer that I have, theta 1 is 2.5 degrees Celsius and theta 2 is minus 15 degrees Celsius. These are the answers that we are looking at. I'm giving you a minute to note this down. Let's move ahead. We solve this one. Let me move on to this one, and I need an answer fast. Two rods of same length and material given amount of heat transfer a given amount of heat in 12 seconds when they are joined end to end, but when they are joined lengthwise like this, how much time they will transfer the heat? You will have 2 minutes to give me the answer.
Sir, it is 3, sir.
Yes?
3 seconds.
You have taken a lot of time to give me the answer. This is not such a difficult question that should take so much of time. Taken a lot of time to solve this question. Not required. Initially, the rods are joined like this. If I call the resistance as R and R, the total resistance becomes 2R. Then the rods are joined like this, R and R. They are joined in parallel. So the effective resistance becomes R by 2. The resistance becomes 1 by 4 times. The resistance becomes 1 by 4 times. The resistance becomes 1 by 4 times. Yes or no?
Yes, sir.
So the time taken would be more or less? Less. 4 times less.
Less.
That is the answer. It should not have taken so much of time. Do we understand this? Should not have taken so much of time.
Yes, sir.
Do it fast. Remember, all these are simple questions on electric current as well. So you can take them as question of current or whatever you wish. This is the next one.
Sir,
Do it.
one more doubt in the last question.
Yes.
Under same conditions means ends are at same temperature, sir.
Yes. Ends are at the same temperature.
Okay,
Okay.
sir.
This one. I'll give you 2 minutes to give me the answer for this one. Option A, 75 degrees. You can straight away put that formula that we had made. Yes or no? Temperature of the interface. For two rods, the temperature of the interface. What was the formula of temperature of interface?
It is
K1
K1
A1
by
by
K1
L1
by
into
L1
theta 1 plus K2 A2
K2
by
by
L2
L2
into
theta
theta 2
by
divided by
K1 by
K1
L1
A1 by L1
L1 plus
plus
K2 A2 by
K2
L2.
A2 by L2. You can just put the formula, get the answer, and stay happy. This is the next one. A cylinder of radius r made up of material thunder conductivity K1 is surrounded by a cylindrical shell of inner radius r and outer radius 2r made up of thermal conductivity K2. The two ends of the combined system are maintained at different temperatures. There is no loss of heat across the cylindrical surface and the system is in steady state. The effective thermal conductivity of the system is, as I said, I've seen question of effective thermal conductivity. This is the question. I'll give you 2 minutes to give me the answer. Well, this is the diagram that I've given for you so that you can solve the question and give me the answer quickly. Wait for 1 more minute. So, as you can see, these two cylinders are in parallel combination. Yes or no? And for parallel combination, we have already made the formula of effective thermal conductivity K1A1 plus K2A2 divided by A1 plus A2. Yes or no? A1 is the area of this, which is pi r square. A2 is the area of this, cross-sectional area of this. So that will be equal to pi into 2r square minus pi into r square. So this becomes 3 pi r square. You can just put the formula and get your answer. The answer that you are going to get will be K1 plus 3K2 divided by 4. That is option number C. I hope you have understood how I have done this.
Sir, how we can differentiate it as parallel or series?
The ends of the rod are at two different temperatures. What do you mean by that? Are they in parallel or are they in series?
Okay, they are in parallel.
You don't read the question, then how are you going to solve it, beta? Anyway, this is the next question, and I expect answer quickly. What is the answer for this one? What is the answer for this one?
Sir, option B, sir.
Option B, that is correct. R1 theta 2 plus R2 theta 1 divided by R1 plus R2. Everyone understand this? Yes or no?
Yes.
Yes or no?
Yes, sir.
This is the next question. This question came in one of the JEEs, and I'll give you 2 minutes to give me the answer.
Sir, it's 60 degrees, sir. B.
It is 60 degrees B, that is correct. So how are you supposed to do this?
Sir, B and C are in parallel and
B and
this
C rods are in parallel and that solves the question. Then you can find out the, you can replace these two rods by one rod and then you can apply the formula of interface. Yes or no?
yes, sir.
Everyone understand this or shall I do it?
No, no need, sir.
Then this is the next question. Do it fast so that I can move ahead in life. Three rods of same dimension are arranged in figure with thermal conductivities K1, K2, and K3. Point P and Q are maintained at different temperatures for heat to flow along PRQ and PURQ, which is correct. Heat has to be flown at same rate from PRQ and PQ. Simple question. 2 minutes. Give me the answer. Well, that is correct. So how are you supposed to do this? Remember, these two rods are in series. Yes or no?
Yes, sir.
So you can find out the effective resistance of these two rods. Yes or no?
Yes, sir.
So that if I call the resistance of this one as R1 and if I call the resistance of this as R2, R1 plus R2 will be the effective resistance. Yes or no?
Yes, sir.
And that will be equal to R3, the resistance of the third rod. Yes or no?
Yes, sir.
Then the correct option would be option C. Do we understand this?
Yes, sir.
Everyone understands this?
Yes, sir.
This is the next one. Simple question. I'll give you 2 minutes to give me the answer for this one. 140 degrees is the correct answer. Remember, all these rods are identical. So all the resistance, if you want, you can call them wrong color. All the resistance, you can call them as R, 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 and R. Yes or no?
Yes, sir.
These two R are in series, so it becomes 2R. Yes or no?
Yes, sir.
These two are also in series, so it becomes 2R. Yes or no?
Yes, sir.
This 2R and this 2R are in parallel, so it becomes R. Yes or no?
Yes, sir.
So the effective combination looks like this. This is R, this is R, and this is R. Yes or no?
Yes, sir.
You have to find out the temperature of this point. Yes or no?
Yes, sir.
So what you can do is you can just apply this shortcut. You can call this as R and you can call the other two as 2R. Do you understand this?
Yes, sir.
This is theta 1, this is theta 2, and then you can apply that formula that we had made. Yes or no? So you can get the answer quicker. R1 theta 2 plus R2 theta 1 divided by R1 plus R2. Do you understand this?
Yes, sir.
So from there, I think you are going to get the answer as 140 degrees Celsius. Anyone understand this, or this is one above our head saying bye bye?
Understood, sir.
Bye bye, bye bye, bye bye. Okay. Then comes this one, and I hope you can solve this one also. Three rods, aluminum, steel, and copper are joined in this way. The end of the aluminum rod is 12 degrees Celsius. The end of the steel rod is 50 degrees Celsius. The end of the copper rod is 4 degrees Celsius. You have to find the temperature of the common junction. I'll give you 2 minutes to give me the answer. Yes, anyone with an answer?
No, sir.
So how are you supposed to do this? Let me call the temperature of this junction as T. Let me call the current in this branch as I1. Let me call the current in this branch as I2 and let me call the current in this branch as I3. Then common sense tells me that I1 plus I2 plus I3 will be equal to 0. Junction law, yes or no?
Yes, sir.
Now if I want to write I1, I1 is flowing from T to 50. So I can write T minus 50 divided by the resistance of this part, which is steel, which is 50. Yes or no?
Yes, sir.
Oh, sorry, it is not 50. L divided by Ka.
Sir, they all will be common and they'll be cancelled. No?
Yeah, they all will be common. No, they all will not be common. L by Ka. It has to be, so this K will get multiplied and on the top. Yes or no? K would be multiplied. Are you getting my point?
Yes, sir.
Plus I2 will be T minus 4 divided by the resistance. So K will come on the top and it will be multiplied by the resistance of effective thermal conductance of copper, which is 400. Do we understand this?
Yes, sir.
Plus T minus 12 multiplied by aluminium, that is 200. That has to be equal to 0. From there you can get the value of T, and the value of T that I have is 10 degrees Celsius, and that is your answer. Do we understand this? Yes or no? No or yes?
Understood, sir.
This is the way you do this. I'll give you 2 minutes to note this down. Let me know once you are done. Then you can note down a formula, which is sometimes you can use it. Thermal resistance of a spherical shell. You might be requiring this formula in a lot many cases, so you can just note it down. Suppose you have a spherical shell of inner radius r1 and outer radius r2, like this. Inner radius r1 and outer radius r2, like this. Remember resistance the resistance of this shell is 1 by 4 pi k into R2 minus R1 divided by R1 R2, where R2 is the outer radius and R1 is the inner radius. This is the thermal resistance between the inner shell and the outer shell. Do you understand the meaning of inner shell and the outer shell? Point
Yes, sir.
A is here and point B is here. And K is the thermal conductivity of the material between the two spherical shells. You understand that this is a sphere with a hole, sphere with a concentric hole. Do you understand this?
Yes, sir.
Have you noted it down?
Done, sir.
Then this is the question, sir. Two thin concentric shells made from copper with radius R1 and R2 have a material of thermal conductivity K filled between them. The inner and the outer spheres are maintained at temperature TH and TC. Similar question we did, but that was for a very small spherical shell. Do we understand this? Same question we did.
Yes, sir.
The inner and the outer spheres are maintained at temperature TH and TC by keeping a heater of power P at the center of the two spheres. That was very thin. Here it is thick. Do you understand the difference between the two questions? You have to find out the power of this body. The previous question that we did on similar nature was here. This one. Remember this question? Thickness of the shell we had found out. Very small thickness. This was 1 type of question where the shell was very, very thin. For a spherical shell, very, very thin shell. Here it is a thick shell. So that is the hint that I am going to give you. You have 2 minutes to give me the answer. So how do we do this question? The power P of the point source at the center, the rate at which heat is going is nothing but equal to heat current. Yes or no? That should be equal to temperature difference delta theta divided by the resistance of this shell. You just put the values and get the answer. Th minus Tc divided by the resistance. Resistance is R2 minus R1 multiplied by 4 pi k into R1 and R2. And if you look at this question and the question that we had done previously, the answer is exactly same. In the previous question, this R2 minus R1 was delta X. Yes or no?
Yes, sir.
Thickness of the shell, and in place of r1 r2 we simply had r square because both the radius were exactly equal. So both the questions are exactly similar. One for was for a very thin shell, this one was for a thick shell. Do we understand this, or this has gone above our heads? Saying bye bye, I'm going, bye bye, I'm going, bye bye. Don't stop me, I'm going, bye bye. Bye bye.
No, sir.
You have 2 minutes to note down the answer, sir. Let me know once you are done. Well, then we will write the next heading for this topic and the last heading for today, which is growth of ice on lakes. How does ice form on lake? Now you must have seen, you must have known that ice always forms from top to bottom. Yes or no?
Yes, sir.
That is because from 0 to 4 degrees Celsius, when the temperature increases, the density of water does not decrease, it increases. Yes or no?
Yes, sir.
And that is because the water at 4 degrees Celsius is denser compared to ice, and therefore water remains down and ice forms on the bottom, and ice starts to form from top to bottom. In fact, if you go beyond the ice formation on the lake, you go some distance beyond, you will find that the water is still at 4 degrees Celsius. So the lake will remain warmer inside and ice will only form on the top of the lake. And the conductivity of ice is very, very bad. So once a layer of ice forms and the layer of ice increases, the water still remains because it becomes very difficult for heat to go out from the water because the layer of ice has been formed, and therefore the water inside remains. In fact, at the bottom of the lake, the water is at least at 5 or 6 degrees Celsius. That is how marine life is saved and they survive. So this is how ice forms on lake, and we just have to remember the formula for ice forming on the lake. What is happening is whatever heat is given out, that heat will melt the ice. From that they get this formula of the height of the thickness of the ice on the surface of the lake with time, with how much time, how much layer is formed. So I will not go and how it is uh, achieved. I can just tell you, I will just tell you the time it takes to change the layer from y1 to y2. This is the time it will take for the layer of ice to change its thickness from y1 to y2. Here you must remember what are the terms standing for. T stands for what? Time. What does rho stands for?
Density.
Density of ice. What does K stand for? This is coefficient of thermal conductivity of ice. Do we understand this?
Yes, sir.
What is this theta stand for? This is the outside negative temperature. But with proper sign, we have written it, so we'll take it as a positive value. Outside temperature. Do we understand this?
Yes.
Now remember, once the ice starts to form, ice is a very, very poor conductor of heat, and therefore the rate at which the layer forms will decrease with time. So once a layer is formed, it takes more time to form the next layer of similar thickness. In fact, time is directly proportional to y2 minus y2 minus y1 ka y2 square minus y1 square. Do you see this? It follows from the above equation that time taken to double or triple the thickness. To double the thickness, T1 is to T2 is to T3, 1 is to 4 is to 9. Do we understand this? Time taken to form thickness Y will be, let us say, T. From Y to 2Y, if you find how much it will take from 0 to 2Y, it will be 4 times. From 0 to 3Y, it will be 9 times. Do we understand this?
Yes.
And if I do the other way, and I've seen a lot of question on this, time taken from Y to 2Y, 2Y to 3Y, and so on. You can also find that time from this formula. These are the questions that are going to come. What is the ratio of time to go from 0 to y, 0 to 2y, 0 to 3y? What is the time ratio from 0 to y, y to 2y, 2y to 3y, and so on? Do we understand the difference?
Yes.
I will give you 2 minutes to note this down. Okay, then this is the question, and I'll give you 2 minutes to solve it. Option D is correct. Time taken to change from 1 to 2 centimeters. We had seen this time taken is directly proportional to final thickness y2 square minus y1 square. Yes or no?
Yes.
So first time delta T1 will be proportional to 1 square. The second time delta T2 will be proportional to 2 square minus 1 square. Yes or no? No, yes.
Yes.
So delta T2 by delta T1 will be 3:1. Yes or no?
Yes, sir.
So it will be 21 hours. Time taken to change from, it will be less than, more than 7 hours. If not 4, it is 21 hours. Right. Do we get this? Yes or no?
Yes, sir.
So these type of question, I hope you will be able to solve. Yes or no?
Yes, sir.
Okay, then I will take your leave, and we are done with the first part, which is conduction. In the next class, we will go ahead and we will solve convection, which is not in your course, and radiation, and try to wind up, if we can, radiation. Tomorrow is Friday. By Saturday, in any case, we'll have to wind up this heat transfer. Anyone has any doubt, please let me know.
No, sir.
Okay, then I'll see you tomorrow. Take care. God bless you. Bye bye.
Bye, sir.